Hello there. Here is an example, or some examples that continue with counting problems. These examples are a little more difficult than the previous video that dealt with counting problems. Two examples here. The first one, how many ways can a person toss a coin so that the number of heads is between 4 and 5 inclusive? Okay. Now, what I'm going to do is break this up into two pieces. I'm going to count the number of ways that someone can get 4 heads out of 13 coin tosses and add that to the number of ways someone can get 5 heads out of 13 coin tosses. Let's focus in on that first component. I'm going to think about the number of ways to get 4 heads out of 13 coin tosses. Well, it turns out that that is equivalent to the number of ways to rearrange the following objects. 4 H's, H stands for a head, and 9 tails. Okay, so I've got 13 objects in there. Each of these represents the result of a flip, and I'm basically asking the question, how many ways can I rearrange these objects? Here I've got the 4 H's in the front. I could have them, another rearrangement would be to have the 4 H's in the end or the 4 H's in the middle, or dispersed throughout the T's in any fashion that I can come up with. Well, I want to know how many ways to do this. Well, if you recall, this formula here, n factorial, where n is the number of objects you're rearranging, divided by n1 factorial, where n1 is the number of objects of a particular type, n2 factorial, n2 is the number of objects of another type, dot dot dot, up to n sub k factorial, where nk is the number of objects of the kth type. This gives me the number of rearrangements of those objects, or the number of distinguishable permutations of rearranging those objects there. Now, so let's see here. Applying this formula to this setting here, the number of ways to rearrange these 13 objects is, well, 13 factorial, that's what n factorial is, divided by n1 factorial. Well, the object of the first type would be heads. There's 4 of those, so I've got 4 factorial here. The second object, or the second type, would be tails, and there are 9 of those. So I'd have 13 factorial over 4 factorial times 9 factorial. That equals 715. Now, this is the number of ways to get 4 heads out of 13 coin tosses. I need to add that to the number of ways to get 5 heads out of 13 coin tosses, which is equivalent to looking at the number of ways to rearrange 5 heads, 5 H's, and 8 T's. Okay, and that is similarly done as before. 13 factorial over 5 factorial times 8 factorial. And if you reduce that down, you'll see that's 1287. So this is a number of ways to get 5 heads out of 13 tosses, a number of ways to get 4 heads out of 13 tosses. Therefore, the answer, so the number of ways desired that we're looking for is 715 plus 1287, which is 2002. Okay, 10 years ago. Wow. All right, example 2 in a political science class. There's 5 men and 6 women. So I'm going to let this box represent the class. I've got 5 men and 6 women. 4 are randomly drawn to present a topic. Okay, they got to maybe give a presentation on some political science theory. Anyway, what is the chance that at least 2 of the students selected are male? At least 2 of the 4 students selected are male. Okay. Now, so I'm going to start off here. That's what we want, the probability that at least 2 of the 4 are male. This is the event of interest. All right. Well, how can that happen? Well, this is an event that can be broken up as a union or statement using ors of other events. This is equal to the probability that, think about what the event, at least 2 of the 4 are male. That could be exactly 2 of the 4 are male, or 3 of the 4 are male, or 4 of the 4 are male. That's what we mean when we say at least 2 there. So 2 or more. So I'm going to rewrite that in those terms. So this is equal to the probability that 2 of the 4 are male, or 3 of the 4 are male. Notice this is different than at least 2. This is exactly 2 of the 4 are male. This is at least 2. There's a difference there. Lastly, I would have or 4 of the 4 are male. I'm running out of space there, but you get the idea. Now what I'm going to do now is, if you look in your textbook at probability law number 6, when I apply it, the law is represented in terms of 2 events, but here I've got 3 events, and that law works out for 3 events as well. It says that if my 2 events are, let's see, what does it say? That law says if A and B are mutually exclusive, that means the events cannot happen at the same time, or if you think of them in terms of sets, they have no common elements. If A and B are mutually exclusive, then the probability of A union B, sometimes we say or, is equal to the probability of A plus the probability of B. Okay, I'm going to extend this idea to 3 events. I can do that because I've got 3 events that are mutually exclusive of each other. If this happens, this cannot happen. If this happens, this cannot happen. If this happens, this cannot happen. So these are mutually exclusive events. I can think of these ors as unions. And so applying this law here, I'd have the probability that 2 of the 4 are male plus the probability, right? The probability of one event union another event union another, a third event would be the sum of the probabilities of the 3 individual events. So next I'd have the probability that 3 of the 4 are male plus the probability that 4 of the 4, all of them, are male. Okay, so I've got 3 events. If I can compute their probabilities individually, add them up, then I've got the probability of interest here. Okay, so I'm going to scoot this equal signs over to give me some space. But this equals this first probability here. Well, if I've got 2 of the 4 are male, that means I'm pulling 2 out of the 5 from the class to be male, and I'm pulling 2 out of the 6 women in the class to be on the rest of the group that are selected to present the topic or some topic. So I've got to figure out the number of ways to have two of the 4 that are male, and that occurs by taking, that's the number of ways to have 2 of 5 that are male. That is, when I say 2 of the 5, I mean 2 of this 5 that I'm pulling out of the class to begin with. This 2 of the 4 is out of the group that was created when 4 were randomly selected from the class. Okay, so the number of ways to have 2 out of 5, multiply that times the number of ways to have 2 of 6 females. Okay, right? I'm choosing, there's 6 females in here, or women, I should say. Um, uh, and that, when I take the product, the number of ways to have 2 out of this 5 times the number of ways to have 2 out of this 6 gives me the number of ways I can have 2 out of the 4 from this group that's drawn there. This is using the counting rule. If I divide this by the number of ways to have 4 out of 11 students, then that would give me the probability. And I'd be using the property that says if we have an equally likely sample space, the way you compute the probability is you take the number of ways this event can occur, which is this product here in the numerator, divided by the number of ways, or the number of possible ways that the experiment can occur, or in other words, the number of outcomes in the sample space. Now, okay, so this ratio gives me this first probability. Now I would do a similar thing for this probability. I'm not going to write it all out. And I would do a similar thing for this probability here. Okay. Now, computing this right here, the number of ways to have 2 out of the 5 that are male, that would be the number, that would be 5, choose 2. 5, choose 2, times number of ways to have 2 of 6 females, that would be 6, choose 2. The product there gives me the number of ways of having 2 males and 2 females on a group, or in a group there. Now the number of ways to have 4 out of 11 students is 11, choose 4. Okay. Add that to this probability. This ratio here would be, okay, the number of ways to have 3 of the 4 males. That means out of the 5 males I'm choosing, 3 of them, out of the 5 here, 3 of them are males, and out of the 6 females, 1 of them is a female. That ends up in this group. So this group reflects, okay, exactly 3 males and exactly 1 female. This times this gives that number of possible groups. Okay, and again, divide that by the number of ways to have 4 out of 11 students. That would be 11, choose 4. Okay, then lastly, add that to the probability that I get that 4 of the 4 that are selected are males. That is 5, choose 4, times 6, choose 0, over 11, choose 4. Number of ways to have 4 males out of the 5, number of ways to have 0 females out of the 6. This group is necessarily all males, which is why there's a 0 there. Okay, so if you take the product here, or if you take these ratios, you get 150 over 330 plus 60 over 330 plus 5 over 330, and that equals 0.652. So the chance is pretty good, a little more than 65%, that at least 2 of the 4 people in the group will be males.